Okay, so I want to derive the mother of all motion equations. Okay, I think it's really important that we know where this equation comes from. Let's see, do we have enough time? Yeah, we do. We have enough time. All right. So what I'm about to do is I'm going to derive the equation. And I want you guys to realize that this is something that I think is very, very important. What makes physics physics is not taking some equation that we don't know where it came from and then just using it and getting an answer. Physics means figuring out where the equation came from. That's what makes physics physics. So Austin just asked if you need to write this down. Well, let me just say this. What I'm about to do might possibly be a question on the test that we're going to take in less than 2 weeks. Wink, wink, nudge, nudge. Okay. So Austin, I'll leave it up to you to decide whether or not you want to write it down. But one thing I will tell you is that I am recording this and I am going to post the recording on Canvas. So if you want to just kind of watch and not worry too much about taking notes, but just kind of understand what's going on, and then come back later and watch the recording and get all the little details then, that would be okay. That would be all right. Okay, so I'm going to do this derivation now. So the way I'm going to do it is I'm going to start by just drawing a couple diagrams here. If I have acceleration equals 0, so that means I have constant velocity. Okay. If I were to make a graph of position as a function of time, and I have constant velocity, hopefully you guys are agreed that that graph is going to look something like this, right? Because the velocity is the slope of this line, and if it's constant, then it's a straight line. What if I were to draw a graph of the velocity as a function of time, and it's constant velocity? So what would that look like? Somebody want to unmute yourself or type it into the chat box? What would the graph look like if I have constant velocity and I want to know what the velocity looks like as a function of time? Very good. Horizontal line. That's exactly what it's going to be. Okay? Right. Now, remember the equation distance equals rate times time, which I prefer to write as x final equals velocity times t. That's the way that I prefer to write it. Okay. Well, if I take this graph of velocity versus time and I look at, I make it into a rectangle here, and I look at the area of this rectangle. What is the area of a rectangle? Well, area of a rectangle is height times width. What is the height of this rectangle? Well, the height of the rectangle is the velocity. What is the width of the rectangle? Well, that's the time. So now my V looks kind of like an R. Well, let me change that, make the V look more like a V. Okay. So are you guys agreed then that the area is equal to velocity times time, but if velocity times time is distance, what that means is that the area underneath my graph here of velocity versus time, that whatever area is down here, that area equals my distance. Do you guys will agree with me when I claim that? So I need to see some yeses or no. If I make a graph of velocity versus time, I'm going to get a horizontal line, and the area underneath it will equal my distance. Okay, good. All right, so now if you believe that, then we're ready to take the next step. What if I'm accelerating? But it's going to be a constant acceleration. Okay. So the acceleration is not 0 anymore, so my velocity is changing. All right. So if I make a graph of position as a function of time, right, you guys agree that it's going to look something like this? Because the slope right here, that's my velocity, and then the slope right here has changed. So you see how the slope is increasing? So I am accelerating. Okay. All right. So that's my graph of position versus time. But what if instead of doing that, let's make a graph of velocity versus time? Yeah, Calvin, that's fine. Don't worry. All right. So velocity versus time. All right. Now let's assume that we start off at some non-zero velocity. We don't have to start off at 0 velocity. We can start off with some velocity that we call V naught that is not necessarily 0. And now if our acceleration is constant, that means our rate of change of velocity is going to be constant. So it means that if we're looking at velocity as a function of time, it's going to be a straight line. So after some amount of time has passed, we are now at a new velocity, V final. Okay, now here's the important thing. If it is true that the area under this curve equaled the distance before, then I will say that that's still true. Even though the velocity is not constant anymore, it's still true that the area under this curve equals the distance that we traveled. If you will let me get away with that, then the rest of this is going to be really easy. We can do this just using a little bit of algebra. Okay, so let me clear this to make room. All right, so I need to know the area under this curve here, or under this chart. Well, some of you might have the formula memorized for the area of a trapezoid, but I'm willing to bet that most of you don't. So let's take this trapezoid and break it up into two pieces. So we got a rectangle on the bottom, and we got a triangle on the top. Well, area of a rectangle, that's easy. That's just height times width. Area of a triangle, well, that's easy too. That's just 1/2 base times height. So this distance right here, that's how much time it took. So that means the width of our rectangle is going to be t, and the base of our triangle is also going to be t. The height of our triangle, well, that's going to be V naught. Or I'm sorry, the height of our rectangle. Height of our rectangle is going to be V naught. The height of our triangle, now some of you might say the height of our triangle is V final, but hopefully you realize that's not the case. The height of the triangle is V final minus V initial. That's the height of our triangle. Okay, so if I can just figure out what these guys are and add them together, that will tell me the total area, and that will tell me the distance that we traveled during that amount of time. You good with that? Okay, so then let me just clear some space here. I wish there was an easier way to erase things on Zoom where I could keep part of my screen and just erase the other part, but not so. Okay, so the distance then, which is equal to the area, is going to equal the area of the rectangle, which is V naught times t, because that's height times width, V naught times t, plus the area of the triangle, which is 1/2 base times height, but my base is t, and my height is V final minus V initial. Okay. Are you good on that? I hope you guys are following. And like I said, if you're trying to take notes and you're having trouble keeping up because I'm going too fast, don't worry, because everything that I'm doing here is being recorded. Okay. So let me just make a little room here. All right, so now it's just an algebra exercise. So I'm going to start with the definition of acceleration. Hopefully you guys remember that the definition of acceleration is delta v over delta t. which is v final minus v initial over t. So that's acceleration, right? What if I take this and I multiply both sides by t? You see how that goes away? So when I do that, I get v final minus v initial is equal to at. Well, hey, here's v final minus v initial. So instead of calling it v final minus v initial, let's call it at. So that means that my distance is equal to v initial times t plus 1/2 times t times a times t, which is equal to v initial t plus 1/2 a t squared. That is my distance. You guys good on that? All right. So now let me just take the final step here. I'm going to take this equation. I'm going to make myself a little bit of room here. I'm going to submit a request to Zoom that they make it easier to erase large portions of the screen. Okay. All right. So now, what I'm going to do is what hopefully is easy to understand. So if I want to know what is my x final, do you guys agree that that's going to equal to whatever my initial position was plus whatever distance I moved during the time interval that we had? So if the distance is that means x final equals x initial plus this, which is v naught t plus 1/2 at squared. There you go. That is the mother of all motion equations. Okay. So what we have just derived is a really, really, really important equation. It's this one right here, which I call the mother of all motion equations. We have now derived it. So we now know where this equation came from. So we can now use this equation with confidence, knowing that it is, it'll do the job for us. So I call this one the mother of all motion equations because all of these other motion equations, they can all be derived from this. If you know the mother, together with the definitions here, so everything that's in yellow, okay, these are definitions. This is the mother of all motion equations. So if you know them, then by combining these together, you can now derive all these other equations. So these other equations, these guys down here, I call these the daughters, the daughter equations. This one up here, I call this one the mother equation. And then these guys here, these are just the definitions of acceleration and velocity. Okay, so if you know the mother plus these definitions, it's possible to derive all these. Now, I'm not going to take the time to do that. I don't think it'd be useful, the use of our time, okay? But it is possible to do.